99% of people who attempt this German math Olympiad problem fail because they follow an intuitive path that leads to a mathematical dead end. Here is the problem. We have two very similar equations. A squared minus b equals 133, and b squared minus a also equals 133. There is one specific constraint. A cannot equal b. Most students immediately rely on the brute force method they learned in standard algebra class. They take the first equation, isolate b to get a squared minus 133, and then plug that entire expression directly into the second equation. But doing that creates a massive, intimidating degree 4 polynomial. Trying to solve this manually is a mathematical nightmare that exhausts most students before they find an answer. Olympiad problems like this are tests of perception, not brute calculation. Realizing that this monstrous polynomial is a quagmire is the first step toward finding an elegant solution. Instead of isolating variables, let's make them interact. We stack the identical equations vertically and subtract. This yields a squared minus b squared minus b plus a equals 0. Applying the difference of two squares identity lets us factor out a minus b. Because our initial constraint states a cannot equal b, we cancel that bracket entirely, leaving a clean, linear value. A plus b equals -1. By using subtraction to exploit the symmetry between the two equations, we bypassed the calculation mess and extracted a highly useful relationship. Let's see what happens when we stack the equations again and add them together. Adding straight down yields a squared plus b squared minus the group of a plus b equals 266. We can substitute the sum we just found, -1, into this new equation. The double negative becomes a positive one, and subtracting it from the other side gives us a value for the sum of their squares, 265. To find the individual values for a and b, we need to connect the sum of the variables to the sum of their squares. Using the standard formula for a plus b squared, we plug in our values, -1 and 265, to isolate the product ab, finding it equals 132. Next, we use the subtraction version, a minus b squared. Dropping in 265 and subtracting 2 times 132 leaves us with the final calculation, 529. Creative use of these basic identities allows us to step right over that degree 4 polynomial that stalls most students. This diagram illustrates the final stretch. Taking the square root of 529 splits the timeline into two paths. A minus b equals +23 and a minus b equals -23. We follow the first path by aligning it vertically with our earlier finding, a plus b equals -1. Adding the two equations together cancels out the b variables, revealing the first solution set, a equals 11 and b equals -12. Following the same process for the second path, pairing -23 with -1 reveals the flipped solution, a equals -12 and b equals 11. To verify the logic, look at what happens when we drop the first solution back into the original Olympiad equation. 11 squared minus -12 becomes 121 plus 12, which matches 133 perfectly. The elegance of an Olympiad problem lies in spotting hidden symmetry. Success comes from identifying the fundamental rules that allow the puzzle to solve itself.